So, this is how we can calculate different quantities which are performance parameters or the thermodynamic quantities of different corners of the cycles using these basic equations which are related with energy conservation and mass conservation for closed feed water heater in steam power plant. Now, moving ahead, we might have an arrangement where we are having two open feed water heaters. So, we are basically having a condition where we have expansion of steam taking place from state 7 till state 10, but in between we have two states 8 and 9 from where we are taking bleed from the turbine, and this bleed is, as it is said that it is an open type of feed water heater, this bleed is directly mixed with the water. This bleed is directly mixed with the water, and then this mixture is pumped once and pumped twice, and then it is supplied to the boiler. We would have understood a point over here by this time that if we are having closed feed water heater, then like last case, then we do not have to have multiple pumps, or which are also called as drip pumps. The pumps which are small in size, which are basically the pumps which are supposed to handle the small amount of mass of the steam, will be called as drip pumps, but in case of open feed water heaters we need big pumps which will handle large amount of mass, and as many feed water heaters are there plus one condenser pump. So, since we have two feed water heaters, so two feed water heater plus one condenser, so we need three pumps if we are operating with open feed water heater. Okay. So, in case of closed, as what we have seen last time, here since we are sending the steam back, we are not needing any pump apart from the pump for the condenser. Then the cycle would look like this, where we have our usual pump from 1 to 2, then we will have steam extracted from 9 which is coming with reduced enthalpy, or which is reducing its enthalpy since it is mixing with water from 2, and then resultant state is 3. Then from 3 we are pumping it to higher pressure, then at 4 there is a drip from 8. So, this mass of water is mixing with mass of steam is mixing with water, then resultant state is 5. Then we are having again pump till 6, and then we are adding heat into the boiler from 6 to 7. Then there is expansion from 7 to 8 for the complete mass in the turbine, but later we will take drip of M1 mass. So, we will have only 1 minus M1 mass expanding from state 8 to state 9. Then we have drip at 9 for M2 mass. Then we will have expansion of the steam from 9 to 10 for mass 1 minus M1 minus M2, and the same steam is passed to the condenser. So, condenser attains the mass 1 minus M1 minus M2 for condensation. So, practically what is happening in this case, we are having lesser mass to be entered into the condenser. So, lesser condensation is required. So, we will actually have reduced load of the condenser when we are using with open feed water heater. This is HS diagram for the same thing. Then we are supposed to find out the same parameters as what we were expecting to find out in other case. So, here as well we have to find out pump work. So, we know what pump work is, so WP, which is pump work, and then we know that first pump handles mass 1 minus M1 minus M2, this pump handles mass this, and it rises enthalpy from H1 to H2. Then this pump, it handles mass 1 minus M1 since M2 is already mixed. And then we will have final pump which handles mass 1, and it rises enthalpy from H5 to H6. So, this is what our pump work, complete pump work. Then we have turbine work. In case of turbine work, it is exactly reverse. First turbine handles mass 1 unit or 1 kg. It reduces enthalpy from H7 to H8. Then this is the first part of the turbine. Then second part of the turbine is here. So it deals with mass 1 minus m1 and it expands from H8 to H9. Then third part of the turbine handles 1 minus m1 minus m2 and it reduces enthalpy from H9 till H10. Then this is complete turbine work. We have basically now Q in, and this Q in is for complete mass 1 and it is in the boiler we are having enthalpy risen from 6 to 7. But then we have to find out Q out, and Q out is in the condenser where we are handling mass 1 minus m1 minus m2 and enthalpy is decreasing from H10 to H1. So these are different work and heat interactions for the power cycle. But now we are supposed to find out M1 and also we have to find out M2. So how to find out M1 and M2? So we know that we first have to find out M1, and the equation for M1 is between these. Okay. So we know how to write. Here we have to write like the mass 1 minus m1 at enthalpy H4 mixes with mass m1. This is mass of liquid water mixes with m1 mass at enthalpy H8. This is for steam, and then we get resultant 1 kg of mass at H5. So using this we can find out H4 minus m1 into H4 plus m1 into H8 gives H5. So we have m1 into H8 minus H4 is equal to H5 minus H4. So we have m1 is equal to H5 minus H4 divided by H8 minus H4. So then we would have found out this m1. Now our topic is to find out m2. So for finding out m2, m1 is known to us. Then here the equation is between along this line, where we can as well write 1 minus m1 minus m2 mass of liquid water mixes with m2 mass of wet steam at H9, and then we get 1 minus m1 mass of H3 of the mixture, and then we can put m2 over here, m1 over here, and then we can find out. So we can say that 1 minus m1 into H2 minus m2 into H2 plus m2 into H9 is equal to 1 minus m1 into H3. So we have m2 into H9 minus H2 is equal to 1 minus m1 into H3 minus H2. So m2 is equal to 1 minus m1 into H3 minus H2 divided by H9 minus H2. And then since we know m1, we could put over here and we can find out m2. So this is how we would do the mass and energy balance for open type of feed water heater. Then next is we can have two types of open feed water heater. As what we have said here, this is one way where we are basically doing mass balance, and we are saying that there is complete 1 kg of steam, but M1 goes in this direction. So, in this direction we have 1 minus M1. Then we say that M2 goes over here, then we have 1 minus M1 minus M2. Then instead of that we can have an alternative arrangement where we can say that okay, steam got expanded from 7 to 8, but there is some loss of enthalpy from 8 to 8 dash, such that M1 into H8, this enthalpy which is lost is subtracted from H8, and then we can get H8 dash. So, practically H8 dash is equal to H8 minus M1 into H8. So, we have 1 minus M1 into H8. So, H8 dash is equal to 1 minus M1 into H8. So, then this is H8 dash. That is why we say that we are coming here, then we are going in this direction, then we are expanding again, then we are coming in this direction, then we are expanding. Then here in this manner, if we try to consider, then the representation becomes simple, where we can say that turbine work is H7 minus H8 plus H8 dash minus H9 dash plus H we will say 8 dash 9 dash, then here we will say 8 double dash, and then this is 10 dash. Okay. Then this is expansion from 7 to 8, 8 to 8 double dash, and then we have expansion from 9 dash till 10 dash. So, this is our turbine work, and rest of the quantities would remain unaltered whatever way we found out. And then this is an alternative way by which we can understand. We will understand here that the turbine is completely always dealing with complete mass, and then for that this turbine line is getting shifted towards the left hand side, which otherwise in previous case turbine line was like this, but for mass balance we were sending M1 or M2 mass towards the feed water heater. So, this is one more way to understand. The next is open feed water heater. It is the configuration of open feed water heater. As we know, in the feed water heater we have liquid water which is coming, and then we have steam blade liquid water which is coming from the pump, and we have steam which is bled from the turbine, and these two are mixing in open feed water heater, and then the resultant mixture is passed to the high pressure heater or maybe to the boiler. So, for that all sake we have steam coming from the turbine. This is the path from which steam will come, and then this is the path where we have feed water heater, feed water coming. This feed water heater, this feed water is coming either from low pressure feed water heater or from pump. It can come from anywhere, and then it will get sprinkled in this manner as jets. This steam will interact with this water, and then in this phase steam will get condensed due to heat loss, water will get heated, but either of them will come down and settle, and then this water which is a saturated water would be passed to the high pressure heater or to the boiler. This is or to the boiler. In this phase we can see that the unwanted gases are going out from the water which is coming from the pump. So, these gases would have actually caused problem to the turbine. So, open type of feed water heater helps to remove the unwanted gases from the liquid water, and that is why rather one open type of feed water heater is suggested to be there into the steam power plant. Since it is removing unwanted gases, so it is also called as deaerator. So, open feed water heater or direct contact type of feed water heater, where steam and water are directly touching with each other. So, there are three names for this feed water heater. One name is open feed water heater, second name is deaerator, and third name is direct contact type feed water heater. Now, going back, we can see that in case of closed feed water heater, there are two types as what we had seen earlier. In the previous case, the type what we had seen is called as drain cascade backward. So, this is called as drain cascade backward. Here backward means low pressures. So, we are taking some blend, we are taking some bleed at state 6 of mass m1, then we are taking bleed of mass m2. This bleed is getting enthalpy loss or energy loss due to heat transfer, and it is coming to state 9 from 6, and then from 6 it is sent back to the low pressure. So, this bleed is coming back to the low pressure, and in the low pressure this is used to heat further the liquid water, and in this phase it will transfer its enthalpy to the liquid water such that water will go from state 2 to 3. Here when it came from state 6 to state 9, water went from 3 to 4. So, this kind of arrangement where steam, after transferring the energy to the water, it is sent back to the low pressure site or low pressure feed water heater, then such arrangement is called as drains cascade backward. It is not that difficult to calculate the properties over here, and then we can find out properties for drain cascade backward, and those properties are basically related with mass m1 and mass m2. So, here we have 1, here we have 1 minus m1, here we have 1 minus m1 minus m2. So, first we will write for the high pressure feed water heater, high pressure feed water heater, which is this. For this we are having m1 mass at H6 enthalpy. H6 enthalpy is losing its enthalpy to H9. M1 mass is losing enthalpy from H6 to H9, but this is getting helped to raise the enthalpy from H3 to H4. H3 to H4. So, this is for 1 unit of mass. So, by this formula we can find out M1. Then we can find out for M2. For M2 it is little tricky, since we can mention that M2 mass is losing its enthalpy from H7 to H11, but we also have M1 mass in enthalpy H10, it is decreasing to H11, but these two enthalpy decrements are used to heat the gas of water of unit mass from H2 to H3. So, this is what the mass and energy balance means combined equation would look like for the low pressure feed water heater, and that is how we can find out M2. Here then we can use this to find out turbine work. Turbine work is unit into H6 H5 minus H6 plus 1 minus M1 into H6 minus H7, then plus 1 minus M1 minus M2 into H7 minus H8. We can understand here that due to such bleeds M1 and M2, we rose the enthalpy of water from 2 to 4 and we went very close to the boiler pressure, saturation condition. So, we reduced this much amount of sensible enthalpy or sensible heat which we would have otherwise added. So, this is how we reduced the external irreversibility and we improved the mean temperature of heat addition. Then instead of that, there is one more arrangement and it is called as drains pumped forward. So, now here we are not putting the water which is saturated water which is obtained after heat loss of the steam to the feed water. That water, instead of putting it back, it will be pumped forward. Forward means from low pressure to high pressure, and such pumps are called as drain pumps. So, we can see that from 2 a drain is coming and then this drain of mass M1 is losing its enthalpy, but after losing the enthalpy it is coming over here. It is a dry saturated liquid and this liquid is pumped using the drain pump such that it will attain the boiler pressure. Same thing, we have M2 mass bleed and this bleed is having reduction in enthalpy and then it will become dry saturated liquid, and this dry saturated liquid will be pumped from low pressure feed water heater to the pressure of high pressure feed water heater. So, the diagram as what we can see, this is the initial part of turbine 1 to 2, but at 2 M1 mass will be coming out, at 3 M2 mass will be coming out, and then at 4 for the condenser we have 1 minus M1 minus M2 mass. What will happen is this 1 minus M1 minus M2 mass will get pumped to the boiler pressure 6 H1 is equal to H6, it is a boiler pressure. So, water will be at boiler pressure. So, from 6 it will get heated and then it will come to state 7, it is like that, but it is going to get mixed with the pumped water at 14 and then we have state 8, and that is how it is getting little complicated for finding out enthalpies. Then we can find out here, since we have M1 mass of bleed, M2 mass of bleed, we can write down for high pressure feed water heater, we have M1 mass of bleed at enthalpy H2 is is giving its heat to the water and it is losing enthalpy to H11, and that water is basically 1 minus M1 mass of water is rising its enthalpy from H9 H14 to H9, okay. But then there is a high pressure drain pump. So, we have high pressure drain pump which has pump work. We will say this is pump 1, this is pump 2 and this is pump 3. WP3 is equal to H12 minus H11. But now we have liquid at 12 at boiler pressure, and this liquid at 12 of mass, this is handling mass M2, M1. H12 of mass M1 is getting mixed with 1 minus M1 mass at H9, and resultant unit mass will be formed at 10. So, the 10 is the state where we are having low temperature feed water getting mixed with the high temperature drain, and then we can go to the low pressure feed water heater, and in case of low pressure feed water heater where we are having M2 amount of mass, we can write down here the energy equation. M2 amount of mass is losing enthalpy from 3 to 13. In this case, water is getting enthalpy risen from 6 to 7. So, we have 1 minus M1 minus M2 mass of water rising its enthalpy from H6 to H7. Here M1 is known to us using this formula. We will put M1 over here and then we can find out M2. But then we have to find out state 8 also. How state 8 is obtained? We are saying that there is a pump which is 2, it is a drain pump which is handling mass 1 minus M1 minus M2, sorry, it is handling mass only M2, it is a drain pump, and this drain pump, since it is handling mass M2, it is rising the enthalpy from 13 to 14. Then this enthalpy 14 of mass M2 is mixed with 1 minus M1 minus M2 mass of liquid water at enthalpy 7, and then we have 1 minus M1 mass at enthalpy 8. So, this is what energy balance we can obtain. So, this is how we have to obtain point 8, and then we can state that Q in amount of heat added is H1 minus H10. H1 minus H10. Q out would be very simple, 1 minus M1 minus M2 into H4 minus H5, and WT is as usual, we have 1 unit into H1 minus H2, we have 1 minus M1 unit into H2 minus H3, then we have 1 minus M1 minus M2 mass into H3 minus H4. So, this is how we have expansion to find out WT. Then we can find out WP. WP is equal to 1 minus M1 minus M2 mass is getting pumped from H6, H5 to H6, but then we have M2 amount of mass at low pressure feed water heater which is getting enthalpy risen from H12, H13 to H14, plus we have M1 amount of mass which is a drain mass, it is rising the enthalpy from H11 to H12. So, these all are pump works, and then we can find out W net, and then we can find out the efficiency. This is how we can proceed for the drain pump forward case. This is a typical feed water heating arrangement. In the typical feed water heating arrangement, we have basically one pump which is open type of feed water heater as we have suggested, and necessity of this open type of feed water heater, it will mix directly the steam, it will mix the, basically this is a closed feed water heater of open type, and this is a closed feed water heater of drain cascade backward. But if we have multiple type of feed water heaters, then we can use one feed water heater which is open type of feed water heater. But this diagram specifically suggests that we can remove the requirement of pump, as what we can see lastly. We can see here that we are, since using two feed water heaters, we need two pumps. One is low pressure feed water heater pump and other is high pressure feed water heater pump. So, these two pumps were required apart from the, this pump and this pump, or in other way this pump and this pump. These two pumps were required if we are using drain pump forward case, but if we use drain cascade backward, then we do not need any pump. We are having throttling process which is an isenthalpic. So, this mass is throttled to reach the same enthalpy, but at lower pressure, then by which we have avoided the use of one small drain pump. But lastly also we could have sent it back as a drain cascade backward, but if we sent like that, then this will increase the requirement of the condenser, and by that means we need a bigger condenser since it will handle more amount of mass. So, to avoid this, instead of sending it backward, last feed water heater is closed feed water heater with pumped forward. So, before that we can use any feed water heater basically of type which is cascade backward, but last feed water heater, lowest pressure feed water heater should be open type, or which should be pumped forward type. Open type of feed water heater, one has to be there to remove the unnecessary gases from the water, but last feed water heater should be at least the drain pumped forward such that it will not reduce the load on the condenser. So, we can find out the properties over here in the same manner as what we did in earlier case. In earlier case we used the energy balance, and then from that we found out. So, same way we have to do energy balance here as well to find out different states. So, here for example we have steam coming from 2 and then it is coming over here and then it is state 11. So, m1 mass of steam from state 2 to state 11 is state 2 is losing enthalpy to 11, and across which we are having increment of enthalpy . But this is for high pressure feed water heater, but for low pressure feed water heater we have m2 mass is losing its enthalpy from 3 to 8, and then across which 1 minus m1 minus m2 mass is gaining the enthalpy from H6 to H7, but it is not stopping. The work of the low pressure feed water heater is not done. Then there is a drain pump which is WP2, it is pumping it from low pressure for mass m2, low pressure to high pressure where it is rising the enthalpy from 8 to 9. Then m2 mass of water at state 9 is mixed with 1 minus m1 minus m2 mass of water at state 7, such that we have 1 minus m1 mass of water at state 10, and this is what it is used over here, and this is how we can find out the different corners of the cycle or properties for the different corners. Here one more thing, Q in is basically 1 unit into H1 minus H12, and here okay, there is one more thing here we have forgotten. We have to remember one thing, that this is drain cascade backward. So, m2 mass is losing its enthalpy for low pressure feed water heater. We have to state like this, m2 mass is losing its enthalpy from H3 to H8, but there is m1 mass that is also losing its enthalpy from a point, suppose A, HA to H8. and these two are hitting the water from of mass 1 minus m1 minus m2 from the state H6 to H7. So, this is rise of the enthalpy from here, but here we are having two masses. One is m2 mass which loses enthalpy from here to here, and then m1 mass which loses enthalpy from here to here. And then we have to say that the pump WP2 will be handling two masses, which is m1 plus m2, and then it is basically pumping them from 8 to 9, and then we have m1 plus m2 at state 9 is mixing with 1 minus m1 minus m2 at state 7, and then we have H10. Okay. This is how we will have to calculate. Now, what are the different components of a feed water heater? There are different components of a feed water heater. If we are having a low pressure feed water heater, then in the low pressure feed water heater we initially will have only condensation process. So, it will have only condensation. So, the steam will lose its enthalpy from one point to other point along the direction, but water will gain its enthalpy from one point to other point. This temperature difference, which is termed as TTD, and TTD is defined as is saturation temperature of blade steam minus exit water temperature. So, if we are having low pressure feed water heater, then this TTD is always positive, since steam saturation temperature is more than the exit temperature of water. But if we go to some intermediate pressure level, then we might not just have condensation of steam, but we would have drain cooling also. The water would reach the saturation liquid state, but further it has still higher temperature, so it gets cooled while losing the enthalpy to the feed water heater. So, steam is losing its enthalpy from here to here, where we initially have condensation and then we have subcooling, but water will get rising its enthalpy from here to here. So, the one part is condenser, one part is drain cooler, but still here we are having TTD as positive. However, if we go to high pressure feed water heater, then the feed water is rising its enthalpy from here to here, but in this process we have bled the steam from high pressure. So, it is also at superheated state. So, initially it will have to lose its superheat. So, it is a de-superheater. Initially steam will lose the superheat, so it is a de-superheater, then usual condenser, and then the drain cooler. So, high pressure feed water heater will have three components: de-superheater, condenser and drain cooler. Intermediate feed water heater will have two components: condenser and drain cooler, and lowest feed water heater will have only one component, which is called as condenser. So, effect of feed water heating. The primary effect of feed water heating, as we can see, since we are eliminating the economizer, increase in efficiency and decrease in heat rate, that is obvious in case of feed water heating. Then since our turbine work is reducing, since we are taking some mass out from the turbine, we have decrease in turbine work output, so we have increase in specific steam consumption. Further, good point of this feed water heating is we need smaller condenser, since it is reducing the load on the condenser. Here we have one more thing: for the same heat input, turbine work output reduces, as what we have seen for the specific steam consumption. So, this is what we have talked about the case where we are having regeneration with feed water, type of backward or type forward, or closed or open type of feed water heating, and these are the advantages of regeneration. So, here we end our discussion initial part on Rankine cycle with feed water heating. We have seen that feed water heating has been opted to improve the efficiency of the cycle, and that idea was fetched from the Stirling cycle, and in the Stirling cycle we were taking the heat from one part of the system and putting it into the other part. So, this heat is not the external heat addition. The same concept we have seen that how to implement into the Rankine cycle. By that means we are reducing the load on the economizer, and we are putting the feed water's temperature or enthalpy close to the saturation enthalpy corresponding to liquid water at boiler pressure. This would reduce the heat added into the economizer, and this will increase the mean temperature of heat addition, and hence it will increase the efficiency, but it decreases the net work. Let us see the rest part related to the regeneration in the next class. Thank you.